So for this problem, we are asked to do a comparison test or a limit comparison test. Now, how in the world do we determine that this is truly a limit comparison test or a comparison test? Well, notice here that we are asked divergence or convergence for the following series. Now, when you look at it and you say, I don't inherently see anything that I could take the sum of and then thus determine if it's convergent. Although I do see a geometric series idea here, which will come in important later. Notice 2 to the n over 4 to the n. That might come in handy later, which it will. But before we get to that, we just got to go through the process. Can I easily do a divergence test? All right, no. That's going to take too many L'Hopital's rules. It's just going to bring back indeterminate a couple times, and I don't feel like doing all that. I'm quite lazy. Integral test isn't really going to be helpful here. So knowing all these tests aren't going to work, we have one thing remaining. That's going to be comparison test and or limit comparison test. Now, the comparison test says, okay, if you find a function is greater than or less than another function, you might, depending on how the two are related, be able to say it's both convergent and convergent or both divergent and divergent. Okay, so for this one here, to make a comparison, you need to find a function that is either greater than or less than your original series. Okay, so I'm going to rewrite our series Okay, I want you to notice something here. We can derive a geometric series out of this, which would be 1/2 to the n, right? We can pull out this if you think about, well, we're not really pulling it out, we're just kind of ignoring these and the reason I'm doing this is sine is always going to be a constant value, 1 through 5, or 0 through 5, and it's going to multiply this term by something, whereas this one, it's going to be a value 0 through 1, and what that's going to do is add a constant value to our denominator. So we do need to do a little bit of a comparison between both the numerator and the denominator. Alrighty, so this, we'll compare 4n plus cosine squared of n to 4 of n, which is what our denominator is over here. I want you to notice that 4 to the n plus cosine squared of n is just, this term would be greater because we're adding something every time. That's always going to be positive. And therefore, this is a true inequality. However, that's if they were in the numerator. We're taking the reciprocal of this. So that's going to flip our sign here to favor this. So, so far we have this argument. Now I just need to prove the top section, which we can do by saying, okay, 2n sine of 2, 5n, and then compared to 2 to the n. Okay, so what is the inequality here? Well, let me actually grab my graphing calculator. I want to show you what 2n sine 2, 5 of n looks like. Or really just what the sine is doing. So let's set something up here, shall we? So sine of 5x squared. Okay, so when we're plugging in values, it's going to oscillate between 0 and 1. So what happens here is this is going to be less than 1, so it's going to multiply this number by something less than 1 or equal to it, which overall for most n values is going to make this one greater, all right? So like if I plugged in 5 or something, you'd get like 0.17 blah, 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 times 2 to the 5. Okay, this would be 2 to the 5. Notice this value is greater than this value, what this would come out to. So I don't feel like really showing any more than I have to, but just to make the point evidently clear, that this is going to be a greater series than this one. And we derived that because we kind of saw that part here. Okay, so now we need to make a statement about our geometric series. Now remember, a geometric series follows this format. When our index starts at 0, alrighty, and more easily it would be AR to the N. This is our A is just 1, N is simply that. So when we identify a sum, we know that any value greater than 1 is going to make the series divergent, where if we have a value less than 1, it is going to be convergent. And we know here, since R is less than 1, this is going to be a convergent series. Now what this says for this series here is if I draw a graph, imagine this series I'm going to plot as blue. Okay, so this series is going to do something, maybe loop around, but it's going to converge to a singular number. However, this series we know is less than our top series. So it can't ever cross, but it can get really, really close to or just stay below this series here, which I've described as a line on a graph. Now what that means is if I draw this in green, it's always going to have to stay less than our other series in its values, which I plotted as points on a graph. But notice if it's converging downwards, we also know that this series will also converge. So hopefully that idea makes sense. So we can make the following statement. We can say, because one over 2 to the n is greater than 2 to the n sine squared 5n over 4 to the n plus cosine squared to the n. Okay, because this is true, because this statement is true, and the series of that geometric series we've evaluated because this series is convergent, well then our parent series here is also convergent. Okay, so hopefully this idea makes sense. I got the comparison from a geometric series and we found it to be convergent. And our reasoning says because our sister series is greater than always of our parent series, we know that the series 1/2 to the n is convergent. We know that our parent series is convergent. Hope you guys enjoyed this lesson. If you did, please drop a like, comment, and subscribe. I greatly appreciate it. I hope that you have a wonderful day.